In this segment, we'll talk about how to find the transverse Young's modulus by using the strength of materials approach. So we have been saying that, hey, we have to calculate these 4 elastic moduli for a unidirectional lamina in order to do the micromechanics of lamina. And in this case, we are looking at the transverse Young's modulus E2. So this is the representative volume element we will take. This is the same representative volume element we took for E1, but the only difference is that we are now applying a load perpendicular to the fibers, not parallel to the fibers. So that's the important thing to understand because we're trying to calculate E2. The other thing to understand is that if we take any cross section, whether it is in the fiber or in the matrix itself, if we draw the free body diagram, we'll find out that the force in the composite will be same as the force in the matrix. Force in the fiber will be same as the force in the matrix, will be same as the force in the composite. But since the cross-sectional area is the same for all of these, which is, let's suppose if this is LC times H, so if it is FF divided by LC times H will be equal to FM divided by LC times H will be equal to FC divided by LC times H, because the cross-section is the same for these forces. So we can say that sigma F is same as sigma M is same as sigma C. So that's important to understand. If you understand that, then that forms the crux of how to do the derivation. So this is what we have. We know that the displacement in the composite will be equal to the displacement in the fiber plus displacement in the matrix. We're talking about the displacements in this direction here, perpendicular to the fibers. Now, this is all coming from the definition of strain, which is change in length per unit length, and this is all coming from our sigma is equal to E epsilon formula. So this is for the composite fiber matrix, and the reason why we are doing these 6 relationships is right here is so that we can put them into this formula right here. So delta C will be TC times epsilon C, but epsilon C is sigma C by E2, so we get this. Same thing for delta F, and same thing for delta M will be this formula right here. And the reason why we write it like that is because we recognize sigma C is same as sigma F and sigma M because the forces on each cross section are the same, and since the area is the same, the stresses will be also the same, and so we'll be left with only TC by E2 is equal to TF by EF plus TM by EM right there. As that is done, this is the formula which we get, and now we're going to take TC we're going to divide both sides by TC, so we're going to get this and we're going to get this. And as we have already mentioned that this is the fiber volume fraction and this is the matrix volume fraction, and I'll say, hey, how is thickness related to volume fraction? We already talked about it, but again, you can see that TF, and let's suppose if I call this to be LC, TF LCH divided by TC LCH. This is the volume of the fibers, and this is the volume of the composite, right? So if you divide, you're multiplying by both the numerator and denominator by the same quantity, but this gives you the volume, and this also gives the volume of the fiber, volume of the composite, and hence it being the volume fraction of the fibers. So you get a reciprocal relationship which will relate your transverse Young's modulus to the Young's modulus of the fiber and the Young's modulus of the matrix and the volume fractions of the fiber and the matrix. Let's look at an example. Here we have glass epoxy lamina here. We find these properties from table 3.1 and 3.2 about the Young's modulus from the fiber and the matrix. This is the formula which we just derived. Volume fraction is 0.7 of the fibers, so that leaves 0.3 for the matrix. Young's modulus of the fiber, Young's modulus of the matrix, and that allows us to find the Young's modulus of the transverse Young's modulus of this particular combination. In this diagram, what you are seeing here is that we are plotting E2 by EM, which is normalizing E2 by EM, as a function of fiber volume fraction. And you can see that it does not, the amount of fiber which you're going to put in does not affect the value of the transverse Young's modulus too much till you get to very high fiber volume fractions. And many of these fiber volume fractions greater than 0.8 are quite impossible to get because of the packing. So this is basically to show that most of the contribution for E2 is going to come from the matrix modulus. And we have drawn these lines for different fiber to matrix moduli ratios, just to show you that, hey, even if your fiber to matrix moduli ratio is very high, it takes a very high fiber volume fraction to see the effect of the fiber in the value of E2 itself. So this is a very important figure to see, is that here we are plotting the Young's modulus E2 as a function of the fiber volume fraction, and you're finding out these are some experimental data points, and this is your mechanics of materials approach formula, which is 1 by E2 is equal to VF by EF plus VM by EM, which we just derived. And you can see that there's a big difference between the experimental results and what you are predicting by using the mechanics of materials approach. This figure here is exactly the same figure as this one. The only thing is that the fiber volume fraction scale has been started from 0.45 to 0.75, just to amplify the difference between the experimental results. These are the experimental results, and this is the results from the mechanics of materials approach. They are different. So there are two of the elastic moduli. One is E2, which we just talked about, and there will be another which is G12, the in-plane shear modulus. And in fact, for both of those, the experimental results are not very close to the theoretical results from the mechanics of materials approach. So we have to somehow come up with a better model to use, and that's called the Halpin-Tsai equations. And that's also one of the videos which you're supposed to look at to be able to see that how Halpin-Tsai equations allow us to have these experimental data points closer to the model itself. Not the mechanics of materials model, but the Halpin-Tsai model, you'll see, will be closer to these experimental results. And that's the end of this segment.